So my first lecture was several days ago, so I would like to make a kind of recap of the main points that I touched in that lecture, and also to add some clarifications following some questions. And okay. So this is this one. Okay. So the main point that I started with in the lecture was that with the long-range system, the lack of additivity makes as a consequence that the thermodynamic potential, energy as a first place, but also the other thermodynamic potential, are not linear homogeneous functions of the extensive variables. And then also this lack of additivity has another important consequence, the existence of a new thermodynamic potential that has been called the replica energy, which has this, this definition is given by the entropy minus, energy minus T entropy plus P pressure times volume minus the chemical potential times the number of variables. And what I have put in evidence that for a short-range system which are additive, this is identically zero, so it is not defined, since the first three factors, the first three terms together are the Gibbs free energy, and the Gibbs free energy for additive systems is equal to mu n, so this is zero. And okay, and then this is the differential relation satisfied by the replica energy, and what I pointed out that this is again another manifestation of difference with respect to shorter range systems, since this second, the right-hand side of this relation is identically zero for a short range system, and it is called in fact the Gibbs-Duhem relation that shows practically that these three variables, T, P, and mu, are not independent of each other. One of the two can be expressed as a function of, one of the three can be expressed as a function of the other two. Let me do something before going on. That the way I have introduced this replica energy was the name comes from the way in which it was introduced, doing a kind of mental realization of replicas. But maybe there is another way that can be introduced. I don't know if one can say that it is more physical, but perhaps it is a way in which one can show more directly that it is a consequence of the lack of additivity. So without introducing mental replicas of the system, just let us think of a macroscopic system, isolated. Oh, by the way, all these things that I'm talking about are related to the study of continuous systems, because there is a pressure, volume. For spin system, I mean, volume and number of sites is the same thing. Also, there is no pressure, the definition. So you have to keep in mind that I'm not talking about a discrete system with the internal degrees of freedom, which can be added, of course. You can have molecules with polarization, but they are discrete, continuous systems like gases, liquids, and so on. So this is an isolated system which has a given energy, a given number of particles, a given entropy, and a given volume. So let us now enlarge a little bit this system, okay, in such a way that each of these variables of these quantities has this variation. So let's make that I choose a given number much smaller than 1, and I take that the increase of volume is equal, dV, the increase in volume is proportional to the volume with this factor. The same for the number of particles. And then, after doing this, I adjust the energy such that also the entropy has the same variation. Okay? Now, let's see what is the variation in the energy. I use the first law of thermodynamics. So, with that choice of the differential, this becomes okay. Now, what is this? Now, you recognize that we recall that the Gibbs free energy, which is equal to, now let's consider a short range system, so additive systems. In this case, this is taking the definition of the Gibbs free energy. Okay, you substitute here, and you get that this is okay, just a matter of substitution of this with this. And you get this one. Okay. So also the energy for additive systems has the same variation. And this is what we expected for additive system, because if you increase all the extensive variable by a given percentage, then you have the same thing also for the energy. The same. When we consider long-range system, we do not expect this relation, meaning that we do not expect this to be equal to the energy. Otherwise, we would go again to the case of a short-range system. So this means that for long range, and this is by definition what is called the replica energy. So you see the same relation that I have there. So this is a quantity that, as you can see here, since this is G in any case, and this is G only for short range system, only short range system. So this is 0 when you have short range system, and this is not 0 when you have a long range system. And the differential relation, maybe it's not necessary to repeat it. You find differentiating this and taking into account the first law of thermodynamics, making the cancellation, you get this. Okay, and let me show now a few examples that two very, very, very simple examples in which you can see that this replica energy is actually different from 0 when you have nonadditivity. The first one is actually an artificial model, because this one, I have to choose this one. Okay. Just take a model, an ideal gas in which you artificially add an interaction but when this is when the two-body interaction is constant. So, you are not doing anything to the system, but just to see that the simple addition of this interaction makes the system non-additive, and you get a replica energy which is different from 0. Then I will do another simple example, but more realistic. A mean field, a system that can be treated with, which is treated just with the mean field approximation. Also, I will show you that the replica energy is different from 0. So here, what you have is that you have practically this is taken equal to a given. Let's call okay. This is okay. So we have this additional constant to the energy. Now, okay, I don't remember if I put 1/2 or not. Okay, 1/2. Yes. So now, let's compute this using this relation. This is the potential energy. So E equal will be what you have for an ideal gas plus this additional constant. By the way, this already shows, although for this very artificial model, that this is no more a linear homogeneous function of the number of particles. It is not even a homogeneous function of any order, because we have both a linear and a quadratic term. Then what I need, okay, the pressure will be the same, because of course it will, the same of an ideal gas, because it will not be affected by this additional fictitious interaction. Then I have to take the entropy, that also will be the same of the one in an ideal gas, which is non-interacting. But I just add yes, the let me see if it is no. Okay. Oh, lambda is the thermal wavelength. Okay. Then I think I have all the ingredients. P, S, oh, mu. I need mu. Okay. These are expressions for an ideal gas, so I mean I do not have to compute it again. Okay. If you plug inside that expression, what you get is, if I did not, okay, minus 1/2. And so you see that adding just this simple fictitious interaction between the particles makes the system non-additive, non-extensive, and you get a replica energy. But now I want to show you a more realistic example. This is what just to have an idea. But now let's take a mean field system. A mean field system means that you express your potential energy. Mean field system that is not supposed to be homogeneous in this case. So let's. What is this expression? This is the potential energy is expressed as a function, as an integral of the density. This would be the density which is not homogeneous on the volume of the system times the mean field potential, where the mean field potential in turn is expressed as This is the two-body potential between the particles of the system. Okay. Now, okay. Then we need again the chemical potential. Now the chemical potential is can be obtained making this kind of reasoning. First, I introduce the component coming from the fact that this can be considered an ideal gas embedded in an external potential. Also, although this external potential, the mean field potential, is made by the particles themselves, so it is not really an external potential, but it is obtained self-consistently by the density of the system. So, if I generalize that, I get that the first contribution coming now also the ideal gas contribution to the chemical potential will be function of the position. I just take a generalization and that for non-homogeneous systems. Okay. To this, I had to add to get mu. I had to get plus the mean field potential, because it is an additional energy that you have to add to the system. You see that I did not put any Q dependence on this, because this one must be constant in order for the system to be in equilibrium. Integrating this on dq, you get n mu. Sorry, multiplied by n of q. You get n mu, since the integral of this is simply the total number of particles, E plus equal T. Sorry, I made it. Okay. It is the potential, the chemical potential at position Q. Now I integrate. And I get, after multiplication with the M. Okay. Plus, if I multiply this by n and q and integrate over q, I get twice the integral. Yes, twice. Yes, the potential was with 1/2. Sorry. Okay. Yes. Yeah, there was a 1/2. Okay.
No, I don't think you already have 1/2 in the definition of U.
You had 1/2 in there. Yes. Yes, yes. Therefore, I don't see where I get the 2. Okay. Mu. That's not U. When I substitute, when I plug everything there,
But then you need the, I
so,
get into this in pi of q, and then there's nothing to left there.
Mm-hmm.
Or
Let me see. Yeah. Plus 2u. No, because here you have 1/2, okay? There I have 1/2. If I multiply this by n of q, and they integrate, I get 2.
okay.
No, so the 1/2 was correct in that expression. Yes, okay. Plus here.
Yes, okay, fine. You are ready.
Yeah, okay. Now the expression is no more there. So let's write it again. If you substitute, and you make also this separation in the thermodynamic variables, that you put E equal the ideal gas contribution plus the potential energy, S equal the ideal gas contribution plus the excess entropy due to the interaction, the same for the pressure, ideal gas contribution plus, and the same for the chemical potential, the ideal gas contribution plus mu x, in excess of chemical potential. Now, if you do the calculation, at the end you get that this is equal to the excess pressure times the volume minus u, minus the. Okay. So for the mean field, this is as far as we can go if we do not specify anything about the two body interaction. And now let's make the assumption that the two body interaction, just to get a further, an expression more detailed than that. This is an homogeneous function like this, okay? For this you can use the virial theorem that tells you that this you can find everywhere. Okay? And this tells also that so this is the final expression for a mean field system, non-additive mean field system in which the two-body interaction decays as a power of alpha, but I have to give a very important detail that alpha must be less than 3. I consider three-dimensional system, so that it is what we call a long-range interaction, since it is not integrable. Because you could say, oh, but even if alpha is larger than 3, I get something which is different from 0. Yes, that's true, but the whole procedure is not valid when alpha is larger than 3. I cannot say that the total potential is in the mean field form. So you have to consider that this is only for alpha less than 3. You can add equal if you consider a logarithmic divergence, but you get that for 3 it is 0. So this is mean field system with this potential here, with alpha less than 3. So a real long-range interaction. So these two simple examples show you that really we get the replica energy which is different from 0. Now, let me go ahead with the third point we have already talked about that. Then there was a question about, I remember there was a question about the fact that I still continue to call P, T, and mu as intensive variables, even when we have long-range potential. Let me be a little bit more precise. And again, what I will use is the first law of thermodynamics. Okay, so what we know is that for additive systems, this goes like n, the same for the entropy, the same for the volume, and the particle, the number n obviously, while T, P, mu are of order 1. And that's why they are called intensive. Now, what happens when we have long-range interaction? Practically what you have is that the energy at large values of n will go like n, let's call gamma with generally gamma a number between 0 and 1. Gamma is equal to 1, so n, the energy is proportional to n squared, like when you have a real, all-to-all interaction, it does not depend on the distance. But when you have, for example, something like that, gamma will be for 1/3, so n will be 4. 1 plus gamma will be 4/3. Okay, the same. So let's see what happens to this variable if I want to get, again, this is valid for a large n, but E will not be an homogeneous function of this order of n, because like before, I will have also other term. It would be like considering, for example, a function like that and another function like that. They both behave like x squared for large x, but this is homogeneous and this is not. Okay. Now, what happens is that this will be, S will be still of order n. And, okay. V, of course, also will be still of order n, and n, okay, n of order n. So to get something which is of order 1, then this must be of order, sorry, T of order n to the gamma, P of order n to the gamma, and mu of order n to gamma. But then, let's take, for example, P over n, or better, E over P, will be still of order n. That's why I continue to call them intensive, because the n behavior at large n between the previous extensive variable for the n and the previous intensive variable maintains the same form. So maybe with an abuse of language, I continue to call T, P, and mu intensive, although they are no more real intensive of order 1, but they have an n dependence. But this ratio is still of order n. So the variation of the energy and the other thermodynamic potential is still much greater, much larger than the intensive variable. Okay, I think so. I hope, because there was a specific question on this point on the previous lecture. Okay, then what we also did in the previous lecture was the beginning of the treatment of the ensembles. And I have written down here just the two first expressions. concerning the microcanonical partition function and the canonical partition function. And below, at the end here, I have written the relation that you get by solving with the saddle point method this integral. When beta f is equal to the minus the logarithm of the canonical partition function. And this is what I was mentioning at about the end of my lecture. It's called the Gendre-Fenkel transform. And it has, this is at the real heart of ensemble inequivalence. And let me okay. Why is that? Because the first thing that you have to keep in mind that can be proved, for example, you can find the proof in the book of Ruel, Statistical Mechanics, Rigorous Results. When you feel like reading such a relaxing book, then the function for additive systems, this function has a well-defined concavity properties that this function is concave both with respect to the energy and with respect to the volume. What is the meaning of concavity? That's, for example, if you have a function, if it is continuous, and the derivative, the second derivative are well defined, it means that the second derivative is negative. But the definition of concavity is not restricted to this. You can have to this continuous function and second derivative continuous function. You can have a function like this, which has, for example, a discontinuity here, discontinuity in the derivative. This is still defined to be concave. In fact, what is the definition of concavity that does not need not to take into account the continuity of the derivatives? Is that if you choose any 2 points of the function and you join them, okay, the line is all below. It is all below the function itself. So this is expressed in this. This is x1, and this is x2. Where chi is a number that varies between 0 and 1. So if you vary chi between 0 and 1, this gives you this straight line, and this gives you the function itself here, okay? Now, when we have a relation like that, when we have a relation that of this form, no matter the form of f of x, it could be exactly the opposite of a concave function. It could be a convex. No matter, this is concave in y. Okay. So if we look at that expression here, what does that tell you? That no matter the form of s with respect to E, this is a concave function with respect to beta, the inverse temperature, this beta f. And this is very important because this is the mathematical fact that proves the ensemble inequivalence when you have additivity. Because additivity tells you that the S is concave, but when S is concave, sorry, you have the following. One could ask, can I invert the Legendre-Frenkel transform? Well, not all the times. But if concave, this is possible. That means that if I now define an inverted transform, if that is satisfied, this is equal to this. Otherwise, it is not. So what's the meaning of that applied to our thermodynamic fact? That if this is concave, then I get, as I said, this is concave regardless of S. But if this is concave, I can invert this and get now I'm not writing explicitly the V and N dependence of V. And this is the explanation of ensemble inequivalence for additive system. Why? Because suppose now, let's start with this. Yes?
S could have a convex integer.
S is convex in both in E and V, but now I'm considering the dependence on
But
E.
S could have a convex intruder, but F is always concave.
Oh, if beta F is concave, whatever the form of S.
Whatever the form.
Yes. So, if you have, for example, here. So let's consider systems for which S of energy is concave. How do you compute that? So, and now I'm assuming also the derivative are continuous. If you look for the minimum, you find this relation. That and also okay, this is satisfied because of concavity. And to find the point that satisfies this relation, I just have to take a straight line with slope beta and find where it touches the function S of E. And the property of concavity, it gives you the important fact that this is unique. While if you have, for example, a function like that, and you choose beta, this slope here, you find two different points that satisfy this one. And you don't know a priori which one to choose. But this is what happens for a long-range system, where S of E, the entropy as a function of energy, is not concave. So what happens here now? If I do the Laplace, the Legendre-Frenkel transform of this, I get a function, as I said, which is concave, always, like that, and continuous also. If I do the double Frenkel transform, I go back to here. So you mean, you see, what this means physically is that for any temperature, you find the energy that gives you that temperature when you look when you want to compute the free energy. But then when you invert for that same energy, you find the same for that temperature, you find back the same energy as before. So this is the equivalence, because there is a one-to-one correspondence between energy in the microcanonical ensemble and temperature in the canonical ensemble. While, let's see what happens when we have, if you do this by exercise, you will find that you get something like this. Something similar to what I was drawing before. Here you have a discontinuity where? Exactly at this loop, you see? Let's say, okay, BC. Because at this loop, you don't know which of the two you have to choose, okay? Or said in other words, this equation has two solutions, this E1 and this E2, okay? And for both of them, if you put both of them in the definition of here, the definition beta, you find exactly the same beta f of beta. So that's why the energy that gives you this point is not well defined. In fact, if you transform back to get S, what you get is not the original one. This also you can do it by exercise, but you get something like that. It goes up to that point and go here, then. So instead of this, you will get this function. This is, let me call the double transform. So what's the meaning of that? That if you choose a temperature, if you choose a temperature like this, the system can be in either this energy or in this one. But now it comes another important difference between a short and long-range system. Suppose that you compute your entropy for a short-range system, and at the end of your computation you find something like this, which is something that happens. For example, when you study a condensed gas, not a condensed gas with the van der Waals equation, which is an empirical equation, you find that there is a certain region in temperature in which the isothermal compressibility is negative. And you know that they teach you that you have to do what the so-called Maxwell construction, and that Maxwell construction is associated to a first-order transition between gas and liquid. And why that can happen? Because the system, when you compute this, the system says, oh, okay, but now I can be separated when it is additive. I can be separated in two parts. Here with this, let's say, this energy divided by the number of an energy density like this, and this by an energy density by this. So two different energy densities. So two different phases that coexist. Why? Because like this, the entropy being additive will be a linear combination of the two, and so will be here, depending on the relative volume between the two phases. And this is better because the entropy will be larger than the one that you computed, assuming that the system to be homogeneous. And since the entropy tends to increase to have equilibrium, the system will do that by separating in two different phases and having an entropy like that. So what you compute, that what could seem in a short-range system an ensemble inequivalence, physically it is not, because the system itself will adjust itself to have the same entropy that you get, assuming entropy to be concave, because this is an extreme case of concavity, because we have a portion which is called, which is a straight line. The mathematician called that an affine part of the entropy. But still, if you do the Legendre-Fenker transform of this, you obtain the same that you got when you did this ensemble Fenker transform of this, with the difference that now you can invert this and get back this one. I remember I told in the first lecture, then this phase separation is not possible when you have non-additive, when you have a long-range interaction. Why? This also can be understood physically quite easily, I think. So suppose that you have a system with two coexisting phases, okay? So this is gas, for example, and this is liquid. So very different densities between the two parts. But why is that possible? Because take a particle or a portion here inside the gas. Its density, its thermodynamic behavior will be determined by its surrounding, because there are only short-range interaction. And the same for a particle here in the bulk. So it is physically possible to have two different phases, because the density here, they do not interact, because here is determined by the interaction with the surrounding particle, and the same here. When you have a long-range interaction, this kind of reasoning is no more possible, because the density here will be determined by the interaction with all body of the system, and the same here. So if you take, let's take two regions which are not very far, like they would be close to the boundaries here in the gas-liquid coexistence. There cannot be any difference apart from a smooth variation of inhomogeneities between the two, because both of them are determined by the interaction with the whole body. So there cannot be a sharp transition of density, for example, between the two. And that means that the phase separation, when you have a long-range interaction, is not possible. In turn, that means that you cannot say that the system will do like this and have a larger entropy here, dividing by two. The system is forced to be homogeneous, or slowing variation, like, for example, in a gravitational field. And so it will really follow this one in the microcanonical setting. If you say, okay, my system, I give it this energy, it will have this entropy, and it will stay here. Seen from the point of view of the canonical ensemble, this system does not exist. So let's see if I can make another picture here. Okay, I want to show you that the system, also another physical argument. Okay, so let's select that. When you have that form, and you take the temperature, which is defined by you find that there is a region in which you have a decrease of temperature which, when you increase the energy, negative specific heat. What happens if you put this in contact with the thermal bath? Okay, let's assume that I put this system, which was previously isolated, in contact with the thermal bath at this temperature here. Okay, in which in the microcanonical ensemble we have negative specific heat. What happens? Okay, let's see what. Of course, when there is a bath with which the system exchanges energy, there are continuous fluctuations. So the system gives some energy to the bath and vice versa. Suppose that there is a fluctuation in which some small amount of energy goes from the bath to the system, a fluctuation of this sign. Okay. What happens? The energy of the system will be a little bit larger, but you see, its temperature then will be a little bit smaller, okay? So, the bath now sees a system with a smaller temperature than its own, so it gives it more energy. So it is not a stable situation. While if it was a larger temperature, then the system will feel compelled to give the energy back to the bath. So the fluctuation will go back. The same if you have this. If you have a fluctuation of this, then what happens? The energy of the system decreases, but now its energy will increase. That means the system will give even more energy to the bath. And again, this shows you that also this fluctuation is not stable. All this is the physical reason because you do the so-called Maxwell construction. All these states are not possible in the canonical ensemble. Either you divide the system like in the short-range case, and then it becomes possible, but at this temperature, not at this one. Or if you have a long-range system in which phase separation is not possible, in the canonical ensemble, what it will happen is that the system will jump from this energy to this energy. So if you keep, in that case, the control variable in the canonical ensemble is the temperature. So if you look the other way here, the plot, you have that you increase the temperature. At a certain moment, there will be a jump in energy, and then you continue to increase the energy. So that's ensemble inequivalence, because while in the microcanonical case, that energy was possible, because it's a control variable. You give it to the system and you will keep it. Here, which is, for example, here, this energy will not be realized in the canonical ensemble. Yes?
So I was asking that, so I understand that why this part is not possible, because if it takes energy, the temperature changes inversely, and that is why it gives more and more energy.
Mm-hmm.
But why this, like, so we are considering the straight line, so there is a part of this curve going up. So why this part is also not possible?
This one?
No, other.
This one?
This. Yeah, this part.
Oh, in fact, that one, yes, you are right. That part is metastable, because if you give it a small fluctuation, it is stable with respect to that kind of argument that I was doing, because I mean the slope has the right sign. But actually, this point here with the same energy has a smaller free energy, so it is favored by the point of view of equilibrium. To go from this to here, it is not sufficient to have a very tiny fluctuation, but you have to give a finite size fluctuation. You have this, for example, when you have a super cool water. If you put the finger, then it will become ice immediately. It is the same kind of. But if you stay very, very quiet and you don't disturb, it will remain super cool, and it will be in this kind of region or here. Okay.
Of course, I mean, this doesn't forbid a first order phase transition in the microcanonical ensemble.
No, it is not forbidden. I plotted, now I gave it in this example in which this is like here. But you could have also a jump in the derivative here, for example. This is will be completely undetected by the canonical ensemble, because it is in the range of energy which is forbidden. Okay, but nothing forbids to have a first order phase transition also in the microcanonical ensemble, but they will be undetected by the canonical ensemble, because they will be in this region, in this plot. Okay. Because you can have also the other situation, but I don't know if I know systems in which this is realized, in which here you have in the entropy this kind of behavior, then you would have that kind of behavior in the canonical, in the free energy. But I don't remember system where this is really what happens. most of the time, I mean, all the times that I remember, you can find the first order transition here in the forbidden energy region for the canonical ensemble. So this will not be detected. In this case, instead of having this one for the microcanonical case, you could have something like this. So a temperature jump in this case, not an energy jump. But you see, undetected by the canonical, because what the canonical will do when you change the temperature as your control variable, you go here, then will go there. Ignoring completely what happens here from the point of view of the microcanonical ensemble. Yes?
Can you please repeat that about the temperature jump for this? Can you please repeat that about the temperature jump?
What happens here? That in specific model, if you do calculations, you can find this situation in which the entropy has what is called a convex intruder, but which is completely continuous, also with the continuous derivative. But you can also find a situation in which in this region there is a discontinuity in the first derivative. Okay, so the continuity in the first derivative is reflected here because the temperature is given by this one. You see, okay. But you see, it is in the region in which the canonical has no states. These energies for the canonical case do not exist. So you will have in the phase diagram, you will have two phase order transition, one canonical and one microcanonical, but in different positions. And now, in fact, this is what I wanted to show you. Maybe without going to the calculation, I just want to show you what happens in a simple system, which is the Tirring model. Tirring model, let me just give you a sketch of what kind of interaction it has. I will skip the calculation, but you can do. I can give you the reference, but okay, they are very simple calculations. Just what is important is that I tell you what is the interaction, the two-body interaction. It was introduced by Tirring in 1970 to have a kind of very, very simple description of a gravitational field. And the main purpose of that work was to show that the fact that at the time, 50 years ago, was found very, very incredible, let's say, that you can have a negative specific heat. You want to show that when you have the system is isolated, you can have that. The people at the time found that very, very strange, because if you apply, for example, if you apply in the canonical potential, they say, no, but why? The specific heat is positive, and also that comes also from the fact that in the canonical ensemble, the specific heat is the expectation value of a positive quantity, so it can only be positive. But then introduce the model to show that if the system is isolated and you compute the entropy, you find something like that, and so the specific heat can be positive, it can be negative. The interaction is very simple. You have a system in a volume, let's say. This is volume. Then you define a smaller volume inside, such that if two particles, if you have two particles here, their interaction energy is just a constant, negative constant. If one of them is outside of, or both of them are outside this internal region, this is the two-body potential, then this is zero. This was a very simple model, but you see that it is non-additive, because if you count the number of particles which are inside here, then this will be proportional to minus n, let's say, n0 square. Because when you sum over I and j, you get this one. So this is a non-additive system. Now let me show Okay, you can compute easily the entropy in the entropy in the microcanonical ensemble. You can do this calculation quite easily, and then you can doing this you can compute the free energy. Doing this calculation, what you find is that this is not concave because of non-additivity, while this is concave. And now I just show you the, okay, this is the phase diagram in which, let me tell you, instead of using a phase diagram, in the phase diagram you have to use the control variables plus possible parameters which are inside the Hamiltonian. The parameters in the Hamiltonian here is, apart from this constant, so epsilon is the reduced energy and eta is the volume. So you can use as your control variables in the thermodynamic, in the microcanonical case, in this isolated case, the energy, the total energy, and you can vary either this or this, and so you can vary this control parameter eta, while the reduced energy was the total energy divided by if I remember correctly, it is not so important, but just to write the right thing. Yes, this one, plus 1. New? No, sorry. I was wrong, of course. This must be a dimensionless number. Okay. So you just separate the... So, in this, in the microcanonical case, this is the phase diagram. What is that red line? Here there is a first order transition, if you cross the line, between a phase in which there are many more particles in the condensed phase, let's call this condensed phase, the condensed region, and when you cross the line, instead, there is a discontinuous jump in the number of particles which are here. We are in a setting, of course, in which the total number of particles is constant, because we are in the microcanonical case. This is, let's call V1 is V minus V0, and N1 is the total number of particles minus those which are inside the V0 volume. So you have a first order transition in the, like that, in which there is a jump in the expected number of particles which are inside the internal volume. The end of the particle is a critical point, like you find in a first order transition which do not break any symmetry, while so this is like in the liquid gas transition. Let's see what happens in the canonical ensemble. They look very similar, but then I will show you something. Now your control variables are no more, are still this Hamiltonian parameter eta, but then instead of the energy you have the temperature. This is a reduced temperature again, because it was better to do the calculation in the reduced ensemble. Yes. You see already, you find that this is, let's say, no more real intensive, because this, if you put it here, is for the n, but energy is for the m square. Okay. Now you have the same. You have a first order transition when you cross this line with a critical point at the end. I mean, the nature of the transition is the same. You have a jump in the number of particles, but what happens is the same that happens there. Instead of having, for example, in that case, in microcanonical case, in the transition, you have a jump in the energy, jump in temperature at a given energy. for the canonical first order transition, you have a jump in energy at a given temperature. In fact, you can see that the inequivalence of the ensemble, if we look at the two ensembles plotted together, once in the eta epsilon plot, eta epsilon graph, and the other in the eta temperature plot. So you see here, you have the first order transition, canonical, and here you have the first order transition, microcanonical. Why there is a region and not a line? Because this is the jump in temperature. So when you, for example, if you increase eta, you have here, there will be a jump, let's say that you increase the temperature here, there will be a jump in temperature at a given point. The temperature will go below, because you see, will decrease. If you increase the temperature in the microcanonical, there will be such a jump here, and then it will continue again to rise. If instead you plot here, you find that this is the first order transition in the microcanonical ensemble, and this is in the canonical ensemble. In this case, you have a jump in energy. You see, the blue region is forbidden for the canonical case, because you jump from here to here. So this very simple model already gives you all the ingredients that I was doing that in the general case. Okay, here maybe I can show you just the last. You see, here there are all the ingredients together. You have temperature as a function of energy, like there. So in the microcanonical, the red one, you have this one. Then it begins to decrease. Then there is a jump here, and then increases again. So there is a jump in the temperature at this particular energy. Instead, in the canonical, you have the Maxwell construction. Increase the temperature. At a certain point, there will be a jump in the energy, and then the energy will continue to increase. So here we have all the ingredients in this simple model that I was showing on general grounds there. And okay, let me give you. I can. Oh, maybe is it possible to raise the, because I don't need it anymore. Nobody's. I had told that before, so I can use the other blackboard. Okay. Okay, the reference. Yes, let me give you the reference for this Stirling model. You can find the detailed calculation there. Okay, so I wanted then to proceed with the other ensembles, because up to now we have considered only the microcanonical and the canonical ensemble. Okay, here. Yes. Okay. When you go from the microcanonical to the canonical ensemble, what do you do physically is that you release the constraint of fixed energy and allow the energy to fluctuate. And the control variable becomes the temperature of the bath. But energy is only one of the extensive variables that you can release. Then you can release also, for example, the constraint of fixed volume. and instead of putting the system in contact with the bath that can exchange energy, you can put it in contact with a bath that can exchange energy, but it is also a moving piston, for example. The bath will have a given pressure, so the system will have to be equilibrated with respect to that pressure. And this is, as from in the canonical case, you release this going to something like this. Let's say putting losing using losing terminology. When you want to release also the volume, you go and you integrate over the energy. You go to something like this. So practically, what do you do when you consider also a fluctuating volume? Is that you take your canonical partition function, which is a function of t, b, and the number of particles. You multiply this by this and integrate over the volume to 0 and infinity. This will be a function now. Now I tell you what is the meaning of IS of T, P, and N. IS stands for isothermal isobaric, because the bath is a bath with a given temperature and a given pressure. Now, maybe when you had your courses, instead of this, which is not very often taught, but what it is very often taught instead is the grand canonical ensemble, in which now, of course, you have already seen many times this. This will be a function of T, mu, and B. So the system is put in contact with the thermal bath with which it can exchange energy and particles, but the volume is fixed, so there will be no pressure balancement between the two. Okay. You can write a more extended form, writing this as a function of the integral over the dynamical phase space of the system, but this is not necessary here. What I wanted, the important point that I wanted to make is the following. Okay, in the first case, in the isothermal isobaric ensemble, I allow to fluctuate energy and volume. Here I allow, to fluctuate energy and number of particles. It is possible to allow fluctuation in all of them. So not only energy, but also volume and number of particles. This would be to build an ensemble in which you do both. And this will be a function of T, P, and mu. But you remember at the beginning what we said, that this tree cannot be, in an additive system, cannot be taken as independent variables. So this, from this factor, you can already guess that this ensemble will not be will be ill-defined if you have an additive system. And you can see that immediately applying multidimensional Legendre-Franken transform. From here, suppose that here you take this as the definition of this new ensemble, the definition of this new thermodynamic potential. If you write, if you do a saddle point evaluation of this variable, of this integral, of this expression, what you get Okay? But then, if you assume that you solve this minimum problem, then you find that this would be divided by beta. For the values of E, V, and N that realize the minimum that, of this expression. But then again, you see that for an additive system, this is G, which is exactly given by E plus PB minus TS. So that would give you 0. So again, we find that for an additive system, this is not defined. Okay? While if this is not true, then this can be very well a thermodynamic potential on the same, of the same dignity of all the others. How much time do I have? About 15 minutes, maybe? Yes. So, okay. Stability. Yes. No, maybe 15 minutes. I would like to do the following because I planned to show something. For the moment, you see, I've done things only concerning equilibrium. But I want to give a connection with the lecture given by Professor Yamaguchi last week, in which he was talking about the Vlasov equation that he was using to study the evolution, the dynamical evolution of long-range system. And he gave an argument to show that, to show that the solution in a finite system go very close to the solution to the thermodynamic limit. But now I would like to touch another point concerning the Vlasov equation in the dynamics. Maybe it is useful instead of giving a few more details on the replica energy, because I think what I told up to now to the replica energy is sufficient to have a first and for that, maybe I can give you an entropy, an entropy. Since the journal is entropy, that was in which the reference that I want to give you to have more details on those kind of calculations. Let me see if I find the reference. Where is it? Well, oh, here it is. So the journal is entropy. There are many details on concave function, application to thermodynamic potentials, positivity or response function, which is something that I touched very briefly in the first lecture. And so it is technical, but you see, it's very simple mathematics, this one. There is nothing. Okay, so let's then, I think it would be nice to have instead this first part, this last 15 minutes concerning the Vlasov equation, and why it is valid for long-range system and it is not valid, it is not a very good approximation for short-range system. Okay, so first of all, how do you get it? The Vlasov equation is a kind of, belongs to those which are generally called kinetic equations, although many, maybe more mathematical physicists do not like this definition because there is no real collisional term, as for example in the Boltzmann equations or in other equations. But nevertheless, it deserves the name of kinetic equation because the kinetic equations are intended to do this. That when you start with your m-body distribution function, and now now with xi, I want to denote collectively the momentum and the position of a particle. Okay, time, of course, time. You know very well that the time evolution of this is governed by the Liouville equation, which is a n-body equation, linear, which has many properties, one of which is very important also for statistical physics, is the conservation of volume. Then, but since it is practically hopeless to have not only have analytical evaluation, but also numerical evaluation, this when n is very large, what people do is to introduce the reduced functions, which are defined. Oh, this is normalized. Integrating out the remaining degrees of freedom, the remaining particle. Okay? As you see, this is no more normalized, since if you integrate this on x1, what you get is this factor. But this is, has been done on purpose to have a simplification in the time evolution, to get rid of those factors in the time evolution of the again I forgot T. Okay, so if you work out starting from the Liouville equation, what is the evolution of Fs, you get, I just write it down because it is textbook material, you can find everywhere, but let me write it. Okay. Sorry. Okay. So what you have, it is still a linear equation, complicated but still linear, in which on the left-hand side you have the interaction between the particles which belong to this S cluster itself. But then you have the collisions with the particles outside this cluster. And of course, this is necessary to have a term like that, because the particles are interacting also with the other, not only within themselves in the S cluster. If you take all the equation together, plus Liouville, this is a closed system, of course, of a huge number of equations, linear, but it is not any more solvable than the original Vlasov equation. So, what the spirit of having a kinetic equation is that you study the first few of them, typically S equal 1 and 2, and try to have a physical way to cut because you see any Fs depends on also of S plus 1. So if you F1 will depend on F2, F2 will depend on 3, and so on. If you cut the system of equations at a certain point, you get a closed a closed system of equations. The price to pay is the following: that the way to cut this the system and to have a physically meaningful way to do it is that you remove the linearity of the system. So what you will get will be equations which are non-linear. So typically, a kinetic equation is one in which you cut the system and then you do some kind of manipulation in which you can get an equation for F1 alone, non-linear. So let's write the equation for F1. You see that one is missing because of this. You have only this term that I can bring here. Okay. Okay. This is still exact, no approximation on this. But it is still linear, but you see F1 is coupled to F2. To get the Vlasov equation, first you introduce the reduced correlation function, which is defined like this. It is a definition of this expression, and now I give you, I show. Okay, this can be a definition of G2. It is called pair correlation function. Practically, you see what it means, that it extracts from this the uncorrelated part. And what one expects is that when Q1 and Q2 are very far apart, this will go to 0 because the two particles will be practically uncorrelated. Now, if you introduce this to this to this equation, which is, as I said, is still exact, you get an equation which is again still exact. Sorry. Oh, I put the mass equal to 1, okay. Let me write this, then I tell you what it is. Okay, I just put this here. Let me write better these two. Okay. What is the Vlasov equation? You get the Vlasov equation when you completely neglect this. Okay. In fact, this one, what is it? Is exactly the mean field potential. You see, it is the mean field potential. So, it's written like this. Again, still there are no approximation. This is still exact. When I begin to do something, I introduce manipulation. So, if I neglect this, I get the Vlasov equation. In other cases, when you want to obtain another kinetic equation like the Boltzmann, you manipulate this one. For example, you know, I think you know very well the Stossel-Ansatz of Boltzmann that gives you an approximation for this, in which you end up with a nonlinear equation for F1. Okay, and here there is the collision term in which there is a nonlinear part in F1 because we have F1 minus F1 taken a different momenta. Okay, so no, I need this. Let's see what happens. To see if the Vlasov equation is good or not, what I need to do is to evaluate the relative importance of these two terms. If this is much more important of this, I can eliminate this and get the Vlasov equation. If this is not true, then I cannot eliminate this. So let's see what happens in the two different cases. Again, short and long range. For this, I just need, what I will do is an evaluation of order of magnitude of all the quantities that appear in that equation. So, for example, for the function f1, this will be the order density times, divided by the cube of the typical momentum of the particle. You can see this, for example, if you take this to be the Maxwell-Boltzmann distribution, you see that this, where n is the density. If you take the density times the Maxwellian, you see that the typical size of this is this one, okay? Then, let's see what this implies for the evaluation of those two terms, okay? Consider first the short-range systems. Now, short-range system means that the the gradient of B has a short range. Let's call R0 range of the potential in a short-range case. Short range of potential. Okay. Now, to compute that, first I want to compute this one. Okay. Now, if this is the range of the potential, if I do the derivative here, I get an integral of the force. Okay, with the sign, I just neglect the sign. Okay, but this will be extended up to R0. Okay, so practically here I have to integrate on a sphere of radius R0. Also, what do I have to take for F1? Since F1 varies on a scale which is much smoother than the range, I can make here in this small range, I can make a Taylor expansion in which this where L is the linear size of the system, and I take a power expansion of this in the small neighborhood of x1. Why is that? Because since this varies very smoothly, if I integrate just taking the first term, I will get 0 because of the symmetry F1 of the symmetry of the force, because if I get an interaction by a particle here of a given strength and I take the other particle at a symmetric position, I will get 0. So what will give me a contribution to this integral will be this part. Now, if you plug that and do an evaluation of what this will give you, you get something like this. if I take F as the typical size of the force, okay? Typical, yes, typical size of the force. I will get this. This will give something like F n and 0 cube. Okay, something like that. Then I have to multiply by the momentum gradient of F1, and the momentum gradient of F1 will give me something like F1, like that. Okay. So this is the order of magnitude of that part. Okay. Now, what happens if I do the same kind of evaluation there? Now, for G2 instead will vary very, very fast. Well, it will not be, because for short-range forces, it is G2 varies on the same scale of the range of the interaction. In fact, for example, for a liquid, you find that G2 is practically 0 when they are very close. Then there will be a very high jump here, and like that, okay, and we'll go to 0. So now, if you do the same kind of evaluation, okay, what I will get for the second term, the term on the right-hand side, what I will get, let me and go to the conclusion. So you see the difference. The difference is this one. So for a short range, the mean field term will give you a contribution much, much smaller than the collisional term. So if you neglect the collisional term, you are doing something completely wrong. Let's go instead to the long-range part, and this is the end. If you do the same kind of evaluation, now the integral in dx2 has to be extended over the whole system, because the range of the force is over the whole system. What would you get is that instead of that expression, you get something with okay, F n V, the total volume, now instead of R0 to the cube, times again F1 over P naught, Okay, this is what? MV is equal to N, the total number of particles. And this, since this was the typical force between two particles, this is the total force of the given particles, because it is one, you multiply the force between given by one particle for n. So this is the total force. If you now do the same for the collisional term, now you have to consider that G2 now is even if you are in a long-range system, G2 will still have a decrease quite fast, maybe not as fast as in the short-range case, but still much faster than the total volume of the system, because the particles, even in a long-range system, become uncorrelated when they are far apart. So instead of this, what you will get let's call this the range of G2. So now you see the situation is reversed for a long-range system. Now the collisional term is much smaller than the mean field term. And so the Vlasov approximation is a good approximation, at least as up to the times in which this smallness will not be taken, compensated by increasing of time, that as Professor Yamaguchi was explaining, that in that case, then collisional term will come into play and bring the system into equilibrium, because as again it was explaining to you, is that if you consider only the Vlasov equation, since there are so many integrals of motion, the system can be trapped, if it is driven by that evolution, to many different stationary states which are different from the equilibrium state. But then when this comes into play, then everything, the collisions will take the system to equilibrium. So I wanted to finish with this because I find often I find interesting when something can be understood on physical ground before doing very detailed calculations. I think as theoretical physicists, this is what we have to do. I think you agree. And but although, in spite of this, many times, several times, the only thing that you can get is by very complex calculation. That as soon as you can avoid to have at least an estimate of what is going on, not the exact values. I'm not going there with this, so you are going to compute the critical exponent, the value of the critical temperature, or whatever. It was just an explanation of why the mean field is valid for a long-range system, and that's all. So okay, so I finish. I will stop here.